So today I'm going to talk about machine translation and specifically about the attention-based neural machine translation. How many of you guys familiar with the deep learning and neural networks? Just like raise your hand. And how many of you work previously with the translation? Okay, cool. So here we're talking briefly about the translation application based on neural network, which use the attention-based models. So I will start by explaining the previous backgrounds that you need to know about the recurrent neural networks, and then I will go through the neural machine translation and attention-based. Let's see how much time that we have and we can go through. So the material of the talk, as you might know, is shared on my GitHub, so you can actually like me open it in Colab or in your local notebook, and you can just follow up the topic. And feel free to interrupt me, but if it's not related to topic and things, so you can keep it at the end, and we can talk later on about the questions. Any questions about the administration of the tutorial or the thing, or should I explain more? You can just go to my GitHub and download the material that I'm talking. It's actually referred to some of the popular ones in the field. So I'm not gonna talk about something if I will not break the wire about anything special out of the main topic. So let's go through background. As you might know about neural networks, that we have some input, let's say there is an image as an input here that is shown by the vector, red one, and you are feeding it to the neural networks the general ones that you know, and you will get an output, which is another fixed size vector, which is shown here by the blue. Here, if you can see. And these kind of so-called vanilla network working feed forward, you will just feed the input as a fixed size. Let's say it's an image, and you will get a classification, or you will get a probabilistic, whatever you like. Engineered on your network. But sometimes you can change the networks to some sort of multiple output networks. Let's say you have the image and you're gonna get the sequence of the words as an output. And representation of words could be one hot representation, could be the string. We're not going into details here. But let's say you have, again, the image as an input, and there is a network. That green rectangle over there is the same network, which is recurrently updating itself. So first it will output the first word for you, which is here, and then it will update the weights, and then again, you will get the second word, third word, first word to the punctuation, end of the sentence. And you can get the sequence of the words as an output. Here we call it one-to-many. Or you can change it to sentiment analytics. Let's say you have the words in a sentence and you're gonna see the polarity of the sentence as an output. So you have the words together as a stream. So you will input the first one. Your sentence is not finished yet. Network will update itself. Then you will feed the next word. Then the network will update itself and you will go in through the last word. When the sentence will finish, you will get the one output as a polarity of the sentence. Or you can change it in the other type of networks like many-to-many. If you have the video, frames of the video, you're gonna get the frames again as an output. Or you have the translation. In translation, you have the words in a sentence and you will get the sentence again as an output, right? And these are a bit like the type of networks that actually works like the second image that you can see here. So there is a network, let's say RNN, recurrent neural networks, which get an input as an X and you have an output as an Y, and the network itself in each time stamp looking at the previous state of the network and update it, and it will go to the next step. So you have the new state as in the previous state, given the new input, and you will update it till the end of the work. These are the type of recurrent neural networks that we have, and this is the simplest formulation of the network. Is it clear? How many of you guys understood 80%, more than 80%? Okay, cool. So if I'm gonna like show them again with some sort of other pictures, in each state you have the input as an X, you have the previous state, your function has your network has some weight, and you have the function to update it. So you will get the previous output, you will update it, and you will get the new one. And the next step you will do the same with the new inputs. And if it's like many to one, so you will get an label at the end here. Or if it's like one to many, you will just put one input, and you will get the outputs in each step, right? Cool. The same for many to many. Or you can actually stack different weights. Rather than having one state, you can have the 3 step. So 3 states can be, again, works as the same. So if you have words as an input, this is the English sentence, and you're gonna get the Portuguese translation. So in each step, you will just like update each of 3 states, and then you will get the outputs, right? There are descriptions you can just follow. And so let's go like the actually tutorial is the background coding to not be like that boring. So I will just follow it up here. I'm afraid to run it here because it's not on my laptop, so I will try. But there is already outputs here, so I ran it before. So you can run it by yourself as well. So first of all, what we're gonna do today is the translation, English to Portuguese, machine translation model, based on the paper, which is popular. I guess it's came out 2017 by Lucas et al. From Google Brain, which is using the attention model. I will go through what the attention model is and how it works, but right now, we need the data, right, to work with. So the data right now, if you might can guess, is the words, right? The English words and the Portuguese words, and they are pair, right? The one sentence has the pair of the translation, and we have the data set of them. So here we have just like is it okay? Okay, nice. So I will use the TensorFlow data sets, and I'm going to use one of the data sets over there. and a special version because I'm using some sort of things related. So plotting for plotting, TensorFlow as always, and logging. So maybe we should just ignore this one because I changed the codes. I'm not using a spicy over. So here, anyone worked with the datasets objects in TensorFlow? Okay, cool. So this function load is downloading the pre-trained models or like the outputs from the TensorFlow zoo. So I'm here we're just like downloading the data, which is the tokens. We will use it then later on. And if I'm going to show you how they look like, when you're downloading them from the zoo, you're good. It's really well-formed text that you can work with. So if I will put the stuff out of the loading, which I'm saving them in examples, it has train and validation for this specific data set. So I will store them in two variables, and each variable is the iteratable function that you can get the words and sentences on. So how it works is just like you can get the batch and take one, so it will show the first three of the examples. And if I will show them here, you will see there is a Portuguese and English translation. So what I have here is the PT examples and English examples, and I'm going to work with them, right? Easy. Actually, it's not that easy if you're working with the plain data, but here we're good because we have these paper data. So any question till here? Everything is clear. Okay, cool. So actually, the thing I didn't mention minutes ago is the network itself is not working with the strings, right? It's a word that you're gonna input it to the network, right? So you should represent that word somehow for the network to understand. So we're using some sort of integer representation of the words. Let's say I have a data set of all English Wikipedia. So I will go through it and find all the unique words in the Wikipedia, and it would be dictionary, right? I will say the first word is the 1, the second one is 2, the third one is 3. So instead of saying A, I will say 1, okay? So here we'll do the same. So we have another like trained model. It's actually literally do the one I told just right now, which is already available in the datasets tools of the TensorFlow. And we will put the English word in, we will get the number. So you can do this like by your own, or here we just like using it, because we're just gonna ignore that details and like going through the network design and work. So here we download it and we just loading it. If you're just like working with the tokenizer, you will just like put the word, you will get the numbers. So here is the sample, you will just like can call it. If you put all the, for example, examples, you will get the numbers instead. So this is the English sentence, you will get the numbers instead of that. So the 72 word is the when in the dictionary. And dictionary is all the data sets. And you can do the vice versa as well, right? You can put, instead of tokenization, you can do the de-tokenization. Okay? Or there are like different things. You can put the ID, you will get the word. Cool. So we load the data set, we changed it to the numbers as an input. Right now, we need some sort of training tricks. So what we're doing here is the array of an input because of the techniques that you might know, because like all of you raised their hand about the training, which is the batch training. So you will put the batch of sentences, not one, maybe 32, 64, and then after that you will update the previous state. Here we had one sentence, right? I just like append them together to make some batch. So instead of one sentence, right now we have like appended text. So good. So what we're doing, as I said, we have the input and we're gonna get an output, which is a translation of the sentence. So there's a giant model here called transformer, which I'll explain more. Let's say we're gonna develop the RNN right now, okay? We're gonna add some stuff in. And we're using this technique to translation, for the translation. So, okay, here it's good. So I need to explain a bit more. Let's say you have the long paragraphs of the explanations. You might be familiar with the gradient vanishing in the networks, in the vanilla networks, like feed-forward networks, which is about vanishing the gradients over there. And something is actually happening in these networks, like RNN, when you have only one W, right? Or we have like a stack 3 or 4 of them for updating. You will see the new word, and you will change the weights based on the new words as in the input. And when the other new word comes, you will change the weights again based on that one, right? And the third one comes, you will somehow not considering the second and the first one, right? You will just like get the third one and you will update the weights. When the first one comes, you will just like get that and you will update the weights based on the outputs. You have like consider labels and you will just like update the weights and to get the better output. Then the first one and fifth one. But actually in translation and the context, the words is related to each other. If I'm gonna say that by statistics, the second word somehow refer to the first one, and the probability is the probability of the second word given the first one. And if I'm gonna calculate the third one, is the third one given the second and the first one. Because the verb is related to the subject and objects, right? So what we're doing is some sort of masking based on the things I just said. So I don't have like something to write here, but I will try to, okay, I will write it here. So you have an input. So let's say these are the integers, that words that you had, and you're gonna make some outputs, right? So what we were doing like second ago was like when we wanted to update these vectors, we were just looking at this one and we were updating the output, and the second time we will doing the same just for the second. But what we want to do and we like to do is when we are updating the weights based on this input, we like to look at the others as well. So there is like some sort of illustration like this that we're gonna also see the others. And when I'm writing them like this, when I'm illustrating it like this, I mean like there is 3 numbers here that you can say which one is more important. Okay, let's say here this one also important, but the next one is not important. Right? But the thing is, this is the idea which I'm coming by, but the thing is here, we don't have the next word. If we are talking about this word, we don't have the next word. We just have the previous words. Okay, I can feed the next word as well, but if I will feed the next word, something happen like the same problem will happen, but in the other direction. The network can be biased based on the next word because it's already know what it will come. So it can just like go and overfeed on the next word. So then the idea of transformer is the mask which is looking at the previous words when you're gonna update the current weight, which is the attention, like the basic attention things that we are saying attention is this vector actually, which says which of the previous words are important for the current updates. If they are important, then consider them as well. There is something else which I might not go dive in, or I might not dive into it, but it's like we need to look at the batch like these 3 or the other 3, and we can do it like in different window sizes. Let's say the other one which is the same. So we have the same layer as the mask and then the feed forward neural network. This is the main core of the transformer. And left side we call it encoder, the other side we call decoder, because it's decoding. After getting the end token, we will just decoding the inputs. Cool. So we appended the text together for the translation. Then we will make the batches for the input of the networks for updating. So for that, we've just like mapped the inputs by these function, make batches. It's just like applying one map. And the map itself getting one sentence in Portuguese and one sentence in English, and it will tokenize it to the numbers, and the other one to the numbers, and then return it. And we will do it in all of them. And that's it. We'll make the batches. Cool. To address this idea, what we're doing is called masking. So let's say the mask is a vector as the size of the sentence. It has 1 or 0. When you will multiply that vector to this sentence, you will get the words in the one positions. So for there, we need to make some mask which you can apply to this sentence. If the mask is in a size of 4, you should just like apply it to the first one and then second 4 words. So we'll make the masks here. And we will go to the next step in the attention itself. If you remember, there was like a mask, then there was a feed forward neural network, right? You should connect these two together. For connecting them, there is an idea how much I should look at the masks, which mask should change during the training, right? So let's say we have the query as an input, maybe this one. Query is the input. We're gonna find the key, which is the new value for the specific type of input, which is V here, right? So let's say we have the sentence, like these are the two first words of the sentence. We have the representation of them. Let's say here we have the numbers. And there is a query, which is the ways that we're gonna learn based on the inputs. And the key is the word that we are working on, the values or the other words. And we will just like consider how much we should change the key based on the input value. Okay? And we're getting softmax on, as always. And there is also the derivative of that in the paper that you can just check. This is making the training possible. But this is the basic formula. So here is the example of the thing I said by the numbers. So here we have different tests on to see how the size of the output can change based on your configuration. If you want to change and see how the outputs are. Till here. Cool. Because we have time, I might mention the multi-head as well. If you are remembering that we had the multi-head in the other side and the attention, simple attention in the other side. So let's say we have an output, first word and second one, and we have the attention. So we can have the different attentions here. We could have different maskings The one could be consider the relation of the verb to the subjects. The other one can attend to the something else, to the colors. The idea is when you're making the next word, it could relate to the different areas, right? So we can, one of these vectors could just consider one of the concepts. The other one can consider the other concept. The other one can consider the third concept. Then we can have the different attention head that you can see here. And when you have this input, you have the concatenate of all of these attention heads together, which is a bigger mask, but they're all independent, right? And for that, also you will change the weights, right? So the size of the weights will change based on each of them should has their own weights, right? So let's say this mask has the initiative weights of 0, all of them, and then during the training it will change. Basically, most of the time we're starting by the random ones, but we'll changing it based on that. And if you'll just like multiplying them, you will get this output. I'm multiplying these two and make this output. And this is the all things in the schema over there. So this is our input. We will convert them to the integers or numbers or representation embeddings, which any representation could shows in the numbers that you can tokenize and you can detokenize. Let's say we have different heads. So you will get queries, keys, and values based on each one. And you will calculate the resulting weights. And then you have the trainable weights that can shows which one is considered or how you should change, how you should look at these numbers as an input. And you will get this output, which is the latent space, or shows how you can use the inputs to the outputs.
So our input data is either main data will be just input of
so
row of digits. So it's not a matrix. It's like matrix 1 by 1.
Okay, this picture actually shows another type of representation. So the question is why this X is the matrix. So this is other type of representation. It's not like 1, 2, 3 or the numbers. So let's say we have a data set only for 4 words. So all the dictionaries is the 4 words. The representation of the first one is 1, 0, 0, 0. The second one is 0, 1, 0, 0. The third one is 2, 0, 1, and 0. And the last one is 0, 0, 0, and 1. Instead of showing it by the numbers, we're showing it them by binary, like one-hot representations. So I'm just like skipping some sort of thing. I'm gonna just give you some ideas in this like short talk, and you can see actually it works here. So let's go for some coding again. So multi-ed attention. Okay, we're making some classes. So each part is a classes, and then we will combine them together as an object, and we will put the objects together to make the layers. So we'll make the multi-ed attention here, same as what I just said. So each of Q, KW, Q query key and value is the layer that you can train, like the Keras layer you might work with before. And you can have difference of them with the different size of batch as an input, the number of the inputs, like the size of the vector of the inputs. And you will dot product that one to the inputs, all of the tensor. So this is the multi-ed attention. We'll use it later. So like here, we'll say we need a layer of 512. So the output of this one is the object of the layers of the cross in the TensorFlow, which look like this, and they're all actually dot products here. So and when you just like apply the TensorFlow training on, you will get learnable weights on. Does it make sense? How many people following me? Hands up. Good. That's good, like almost everyone. So once we have this one, we just need some sequential model as a dance after that one, right? And then we will combine them together as an encoder and decoder. So we have the self-attention, we have another self-attention for the decoder, and also we have the feed forward after that. So what we're doing, we're just like put the inputs here, and then we'll get the outputs. Easy, right? So for that, we just like use the previous one. So we had the multi-ed attention and the feed forward. So we just like combine them together. There is a norm here as well. Let's say just for normalization of the outputs, because they could have different numbers as an output, and the dropout for the training. And the same, and we'll make the encoder layer here. And if you was looking at them, that one is also has the layer size for the dense, for the sequential layers over. And that's still till here. As I said, we can have the encoder decoder together, like. That's one core, so we can have the multiple of them. So after making all of these things, right now we're using an encoder and the decoder. So we have the encoder part and decoder part. All of these inputs are the number of layers, how many encoder you will use, and the number of heads based on the previous class definitions. And you will just combine them together. with another training part. You have the call function, how to use it, how you will just like this is for passing the values in cross, like if you will working with. And we'll call this class right now the transformer, which was the first illustration I've shown you. Good. So I can say, for example, I need one transformer with 2 layers. Each model inside has 512 neurons. And the input vocabulary size is like something, it shows the number of the matrix of the inputs, like the other dimension of the inputs. 0, 0, 1, and 0, the one I said. How many words this transformation can generate between 0 to 255, or how you are representing. Okay, the rest is training. And for that, we need a loss and matrix as well in TensorFlow. So you need a loss and matrix. So we will also define our matrix. And how the loss function works based on the optimizer again. And now we have some giant transformer class that you can get everything. And here you are, you can train it, right? Just the thing is, also you have the training step in cross, right? In each step, how you should feed the data. So you will say the training, using the training step, which has the inputs and the outputs, and how the inputs and outputs works, then you will apply the gradients on, and you will apply the loss and accuracy. And we'll define one epoch. Here, I guess it's like 20, if I'm not mistaken. Or you can change it over. Yeah, I just like change it to 1 here. But you can like train it more if you like to. And here we have the output. If you just like add also checkpoints in the epoch, you can just save the model each iteration. You can use it later. And here is the train model, which could use for the inference time. Good. So basically, for the inference, also we need to write everything again, right? For the decoder parts, right? If encoder and decoder, both of them, if we have the inputs, we're not changing the outputs, but we will multiply it, and then we'll multiply, and then we'll dot products, and then we'll multiply it again by dense, right? So we should write it again here, which we call it translator right now. So if you will put one module, transformer module in, you can have the translator. How the translator works, getting an input and the transformer, and then you can just apply the translation on. And this is the magic. This model surprisingly works very well. Even by maybe 5 times training, which takes like 5 minutes, you can get some outputs, which is kind of really good. We had just like one epoch training. Let's see how is it. Okay, it's not that good. I had like the train model over there in my laptop, but here we can wait 5 minutes, or you can run it by 20 minutes, and you will see the output, which is surprisingly works well. For the rest of the time, I will show you some plots, which is kind of interesting. So what we are doing is, let's say we're going to see how the attentions work. We will get one input word, and we will multiply it by the trained mask. And we will look at the output, and we will see which one making the higher number. And we have different inputs and different heads. You can make one matrix which shows which word related to which head. And then you can make something like this, which says if, and also you can have, again, word by word, right? So you can see which word relate to which word. And here, it's not a good output. Maybe I can go through the GitHub here. I might have the outputs over there. So I will update it by the train model as well. I guess there is no train model there. So, for example, you have this input as an English sentence, and you will get these outputs, right? So, and it shows like esto as an output was related to this. And when the network was making the esto, was looking at this. And when the network was making Libero, was looking at the book, also did that. But you can see it in the different layers as well, right? And for example, here you can see this part, this layer, actually does nothing, maybe just looking at the previous one, like the RNN. But maybe this one is considering something else, right? Or maybe this one is doing, like this one is like maybe the object of the verb, of the sentence, right? So for this one is looking at all of the previous ones, like, but for the other one is not. And you can do is like for the different ones, and you can also save all the translator right now as an inference. So you will just say save the inference translator. We can use it later. Thanks.